Hello everyone. Hello everyone. This is Jinyoung from the University of Tokyo. Today, Ken, Ito, and I would like to make a presentation about auditory and AC frequency characteristics and side effects of piezo-actuators with duplitized conductive polymer nanosheet electrodes. First, we will introduce a capacitor-type actuator, or the auditory air device, fabrication methods, measurements of the various frequency characteristics of the actuators in different sizes, discussion and concluding remarks. Our lab has been searching for ways to transmit auditory information without covering ears to realize a hands-free situation and for safety in the industrial environment, such as assembling factories, delivery services, and inspections of returning airplanes, which requires high efficiency, accuracy, and safety. In 2050, we developed a full ears-free auditory air headset with capacitor-type actuators using piezoelectric film and conductive polymer. As the devices don't cover ears, people can hear both environmental sounds and digital auditory information at the same time. We fabricated capacitor-type actuator with piezoelectric film and conductive polymer. We laminated conductive polymer on both sides of the film. When the audio signal, that is AC volts, is applied, the entire film vibrates by expanding and contracting. This is the actuator. Because of its ribbon-like feature, we call it a piezo ribbon actuator. Let's hear the sounds. Music signal is running from the beginning, but no sounds comes when it's unfolded. When curved, here comes the music. Still, there are some problems with conductive polymer. We use P.PSS, which is strong acid colloid solution and insoluble. Instead of P.PSS, we use self-doped conductive polymer, which is weaker acid and water-soluble. We tried to make a piezo ribbon actuator with this new polymer, but because of its soluble characteristics, we couldn't laminate this on the surface of water-repellent plastic film. So we developed a new processing method. We named it charged-mist laminating method. In this method, the conductive polymer solution is charging with 5 kilovolts high voltage, and the droplets are splaying and dried repeatedly. As a result, the water-soluble conductive polymers are laminated on both sides of the film. However, there were also limitations to make the uniformly laminated samples. It is difficult to control the number of droplets sprayed through an airbrush with a compressor. Then, we introduced to a microgravity coder through collaborative research with the Fujiya Laboratory of Tokyo Institute of Technology. Microgravity coder realized printing the conductive polymer nanosheets on both sides of piezo film uniformly over a large area. We cut the film printed nanosheets into these sides. The longer side is the stretched direction of the piezoelectric film. We fixed this size as a standard sample based on the diameter of 7 cm, which doesn't touch the air lobe when the actuator is curved. Based on the standard size, we fabricated samples changing size to help twice and 3 times. Also, a bulk sample laminated micrometer order with barcoder was prepared for comparison. Next, we evaluate the AC characteristic of those actuators. We apply the sinusoidal voltage signal to the piezo ribbon actuator and measure the current response. First, we measure the frequency response of a standard sample made by Gravity-Accorder with various voltage amplitude. The following are the results of 5, 10, 15, and 20 volts input from the bottom. Peaks appears at about 500 kHz, and nonlinear sigmoid curve is observed, with an inflection point at approximately from 10 kilo to 100 kHz. The average of the current amplitude between audio frequency range from 20 to 20 kHz shows that the current is amplified 5 times greater when the input voltage is increased from 5 to 20 volts. From this point, we expect that increasing the voltage will enhance the audio signal. However, there were no significant increases in the low frequency range. Next, this is the characteristic of the standard size sample made by Bar-Accorder. The inflection point of the sigmoid curve is observed from 100 to 1000 Hz. Let's compare with Gravity-Accorder sample. The inflection point of the Bar-Accorder sample have moved into the low frequency region of the audio range. This result shows that the Bar-Accorder sample has higher output in the consonant frequency range. To observe more details, we divided the logarithmic frequency axis of the same order into 8 equal parts and measured the current response. As expected, the Bar-Accorder sample, which is green line, has higher output in the consonant region. However, the Plateau values are approximately equal. The result shows that by increasing conductivity, only one layer of nanosheet could supply sufficient output without changing thickness of the film. We also observed a double sigmoid curve in the Bar-Accorder sample. The origin of this structure is now under the inspection. At the low frequency that corresponds to the ball range, we couldn't see significant enhancement, even when we changed the thickness of conductive polymer. In general, consonants are important to transmit the meaning, and bold convey speaker's identification, gender, age, and emotion, etc. We examined characteristics in the low frequency range by changing size of the actuator to strengthen bowl transmission. First, we changed the size in the width direction, which is also known to the stretch direction of the piezoelectric film. We prepared half and double width sample from a standard size and measured their frequency response. From the results, there were no significant differences between samples over the entire frequency range. Next, we changed the size in the length direction, which is the same as the stretch direction of the piezoelectric film. We prepared half double and triple length sample from a standard size. The current response is amplified when the actuator's length is increased. Especially for triple length sample, the current is amplified nearly 5 times of the standard size. We think that is because of capacitance, depending on the electrode area. However, when the width changed, we couldn't observe the differences. This behavior doesn't follow the classical electromagnetism. Next, we prepared half and double width actuator with triple length. As mentioned ahead, there was almost no change in current response depending on width. However, at the low frequency range below 100 Hz, the current amplitude of double-width sample is slightly stronger than other samples. In the low frequency range below 100 Hz, which corresponds to the low ball range of male boys, the width extension affects the current enhancement. Now, we compare these results with the model based on classical electromagnetic theory. Let's consider the impedance in the classical LRC circuit model. In the low frequency region, the effect of the capacitance is dominant, where in the high frequency are dominated by resistance and inductance. Nevertheless, the actual measurement shows the behavior of RC circuit. In the following, we consider an IC series circuit by assigning 0 Henry to inductor and 10 kΩ to resistor. In the classical RC circuit model, the high frequency line shows resistive behavior, so the amplitude of the applied AC voltage is proportional to the plateau current value. We then took the plateau current value and plotted them on graph. Although the conductivity is different from samples, it is proportional to the applied voltage in all cases, and the intercept with the vertical axis is close to the origin. From this, it is confirmed that the behavior in the high frequency range well agrees to the one of classical resistance. We next check the theoretical behavior with resistor and capacitor as parameter. As the resistance decreased, the plateau current value increased on the high frequency range, and the inflection point moved slightly to the high frequency side. In contrast, in the model in which only capacitance is varied, the effects of the capacitance approaches 0 farad as frequency increases, so the value of current is determined only by resistance in the high frequency range. On the other hand, in the audio frequency range, the sigmoid inflection point shifts to the low frequency range as the capacitance of the actuator increases. Let's compare with the actual measurements. The upper graph shows the frequency characteristics when we change the length of the actuator, and the lower when change the width. From upper results, the electrodes affects the current amplification, which is well agrees to the model. But from the lower, despite the area was changed, there is no significant difference. We consider the behavior of output based on phenomenological models, dependence of electrodes area of the resistance value. We can consider the possible situation A and B. Dotted line indicates theological model values, and solid line shows the result of actual measurements. In case A, the current amplitude was enhanced with increasing area, while in case B, it decreased. However, any of the classical models explain our actual measurements stay constant value with changing the width. Classical electromagnetic theory assumes free electrons in metals. However, in conductive polymers, holes are generated when electron acceptors pull electrons out from the polymers. So, this hole carries free electrons. We are thinking that increasement of the actuator's length may be related to the absolute number of carriers. Let me summarize this study. Using a microgravity coater, we fabricated a piezo-ribbon actuator, and we expect to reach the level of practical output for actuators by enhancing conductivity. We also observed current amplification when piezoelectric film is extended in the direction of stretching. On the other hand, the size effect with changing the width is hardly observed. This is a different behavior from the classical mechanism. We are considering the quantum effects of conductive polymer, and the research is in progress. In addition to the electrical response, we are also evaluating speech quality with several methods. This is the reference, and we would like to send our best thanks to Toso and CREA Corporation, Fujiya Laboratory, and Dr. Professor Hideki Shirakawa. Thank you very much.